welcome you to this webinar today. In this webinar, I will give you an overview of debugging and tracing of AUTOSAR applications with the UDE, the Universal Debug Engine. I'd like to start with a brief overview of AUTOSAR, in particular the AUTOSAR Classic platform. Then we dive into the debugging topic with some remarks on interfaces between the AUTOSAR and the tool and what is state of the art. And then I'll switch to a demo example, and I'll show you how to do stop mode debugging and also how to do tracing and what you can expect from the tracing. So let's get started. So what is AUTOSAR? AUTOSAR is basically an open standard that defines an automotive software architecture. AUTOSAR defines an interface between the application software and the basic electronic functions of a vehicle. So behind the AUTOSAR, there is a partnership of automotive OEMs, tier ones, suppliers for the automotive industry, and also of tool vendors like PLS. So we are part of the AUTOSAR consortium, and we are involved in the work on debug and trace specific things in the AUTOSAR standard. What is the main goal of developing or defining the AUTOSAR standards? Why the AUTOSAR members doing this? Obviously the main thing is, as always, reducing costs and also reducing development times, and this can be done by reusing of already developed software components and also reusing tools and methodologies. The clue behind this is basically decoupling the hardware and the software so that hardware and software are both independent from each other. The development of a AUTOSAR-based software hopefully increases the scalability of the systems, and you can use your software and transfer functions to different vehicles, different vehicle platforms, and also between different OEMs. That may reduce costs, that increases the software quality, and hopefully helps to fulfill the today's and the future requirements on automotive software in terms of safety, availability, maintainability, and so on. To achieve this independence between software and hardware in AUTOSAR, there is a layered architecture introduced. So shown here in that picture, each layer, starting from the hardware, the microcontroller layer, up to the application layer, each layer creates a new level of abstraction so that the hardware, for example, can be easily replaced without changing the software, and also the software components can be exchanged. There is a system layer here in this layered architecture that may contain a operating system, and that is that we are focusing here. And this operating system and this system level here is based on OSEC. So OSEC is a former standard that was created by German car manufacturers and also suppliers of electronic components. And the principles of OSIC and also the concepts were incorporated in the specification of the AUTOSAR operating systems and also extended. So there are new things here in the AUTOSAR operating system compared to the OSIC, but in general, the AUTOSAR OS is backward compatible to the OSIC OS. When we look at other pictures, then you will find that the layers here typically summarized as basic software. And on top of the basic software, there is the RTE, the AUTOSAR runtime environment. And this RTE provides the interfaces between the application layer and the basic software here. And it also provides functions to provide communication between all the software components between each other. And this communication layer or this communication can either happening between the software components of the same ECU, but also across ECUs using, for example, communication services of the basic software that relies on physical communication channels like CAN, FlexRay, Ethernet, and so on. And from the perspective of the software or the application layer, there is no difference between communicating on one ECU or communicating across several ECUs. The RTE, the runtime environment, acts as a communication bus that spreads across all the ECUs, and that's why it is called virtual function bus. Okay, I think that's enough for now for a general overview of AUTOSAR. Now I come to the question of the specifics related to debugging if you develop as AUTOSAR-based software. If you look at the debug tool, then you will see at the first glance that there is nothing special. From the debugger's perspective, is an AUTOSAR-based application only a piece of software that is running on a microcontroller or an embedded system. You can, in the software, of course, set breakpoints. You can look into the code. You can look into variables in the memory, in registers, everything that you are familiar with if you are using a debug tool. You can also look at the structures and into the variables that are part of the AUTOSAR operating system. But here comes the first but. You have to interpret the meaning by yourself. The second but is the debugger has no knowledge about the tasks of your operating system. However, this is one of the most needed information when you debug your application that is running under control of an operating system that's not typically or it's specific to AUTOSAR. It's also it's also applies to other operating systems or real-time operating systems. If you halt your application, then typically you want to know which task is currently executing your function where the breakpoint, for example, was hit. And for that reason, you need operating system or respectively, in our case, AUTOSAR awareness. So AUTOSAR awareness is a debugger feature. In our debugger in UDE, it comes as a add-in that adds knowledge about the AUTOSAR internal structures and objects to the debugger. Basically, the awareness add-in tells the debugger which memory locations and which variables represent which objects or states in the AUTOSAR operating system. Up to now, the most common way to provide this information to the debug tool is to use the so-called ORTI. ORTI stands for OSIC runtime interface. ORTI defines a file that contains all the necessary information that is used by the debugger to show AUTOSAR specific information. The ORTI file is automatically generated during the generation process of the AUTOSAR application. So where you put all the functional stuff and the operating system together and build your binary. And the ORTI file that can be loaded into the AUTOSAR awareness add-in in UDE. From the ORTI file, the add-in gets all the information about the memory locations of the operating system objects and also the variables, and most important, how to interpret them. But for today's implementations of AUTOSAR applications running on multi-core MCUs, or with the need to analyze the runtime behavior as accurate as possible of your application, the ORTI can only be used to a limited extent and has some disadvantages. The first disadvantage is the lack of standardization. As an example, if you want to analyze the runtime behavior of your system, you will use trace that is provided by the microcontroller. This is a microcontroller feature, and it's a very common technique to observe the runtime of your application without influencing it. And the microcontroller captures trace information, and or the debugger captures these trace information. Then you can analyze the timing based on these trace data by, for example, a timing tool from a different vendor. But if you look at the implementations of different trace tools, then you will see that they are incompatible. You have no interchangeability between the tools, and so it's hard to use different tools efficiently. Trace tools, timing analysis tools. A second disadvantage is the hook mechanism. So what are hooks? So hooks are small pieces of code that are used to instrument the operating system, with the aim that the trace tool understands the various operating system tasks, states, and recognizes the state changes. For example, changing or switch from one task to the other. However, the hooks that already present in OSIC-based systems and also implemented in the AUTOSAR operating systems were too intrusive, and there was a wish to replace them with less intrusive ones and more standardized ones. For that reason, the work on the new AUTOSAR standards or in the present releases of the AUTOSAR standards has also focused strongly on the topic of debugging and tracing. So that was also the reason why we are involved in that. And the result was that the old ORTI was replaced by ARTI, which stands for AUTOSAR runtime interface. The ARTI defines an interface between the build tools and the debugging and tracing tool. It contains basically the same information that is needed for debugging as we have seen for the AUTI, plus some new informations regarding tracing, and also plus support for multi-core applications. Yeah, the file format, it's not that important for you, but the file format has also changed. It's now based on XML. So it is a so-called RXML file, which stands for AUTOSAR XML file. Okay, then let's look into the debugger, how it works for stop mode debugging. Before I go to the tool, I'd like to say a few words about the demo here. I do not use a commercial AUTOSAR stack here or AUTOSAR operating system. I use the Erica OS, which is a free and open source project. We have customized the AUTOSAR or the Erica OS a little bit because it's quite old and does not support the new RT features. But using Erica OS helps me to do not violating the rights of commercial AUTOSAR stacks and OS providers here in such a webinar. As a target device, I use the Infineon Aurix. It's a TC39 mounted on a trike board. I'm using the debugger hardware from us, the UAD2 Pro, which is the basic device for debugging in our universal access device family. And that device is connected to the PC using USB. Okay, and for the target communication between the UAD and the evaluation board here, I'm using the DAB interface from Infineon. Okay, then let's jump to UDE and yeah, open a debugger workspace. I have already prepared one because it would take too long to create one. It's a few clicks, but it's not necessary to bother you here. In the workspace, there's also already the application access already the application that I want to load into the target system, into the Aurix, which is the Erica OS with some small application code here. I flash this to the device, and then I can start the application. We see here some variables are counting up here, so we see the application is running, and I can, for example, set a breakpoint in a demo function here. And we stop at the breakpoint, nothing special. We can look at the call stack, for example. I put this call stack window here. You see, okay, this demo function belongs to a function that could be by name a operating system task. We see here some operating system functions here, which called the task, and yeah. So basically, you can debug here in this environment your application and also some of the operating system functions, but you don't know what happens behind. You don't know which task is currently executing your functions. You can look at the name, but that is not very useful in some cases. That's why we need the AUTOSAR awareness plugin, which has to be enabled using the config menu, add-ins menu, and then click on the AUTOSAR support OT and RT, and then press OK. And with that, you can open now from the Views menu a new window, which is called the AUTOSAR support window. The AUTOSAR support window asks for a description file. I mentioned before there are two ones possible: a ORT file or an ARTI file. To showing you this feature, I'd like to select the ARTI file, which is typically generated automatically by the build environment of your AUTOSAR system. In that specific case, because the Erica OS does not support ARTI by default, we have created this file manually, which is quite a hard job because we have a lot of information that could be integrated in the ARTI file and used to show the operating system objects and states and variables in our ARTI or in our AUTOSAR window. You see here on the tabs, we have different types of information available. For now, most important are the tasks. So we see we have one task running, the others are suspended. I put this on this side to see all the tasks at once. We see also this is a multi-core application, so there are different cores executing the tasks. A better overview you get with the cores tab here. We see all 6 cores of the AURIX are used. At the moment, only core 0 is executing a task. All the other cores are in running the idle tasks here at this breakpoint. If you create the ARTI, for example, with a commercial AUTOSAR system, then you may get more information, but for now, because we have done this manually, we have only information about the task stacks, the alarms, which are counters here in the AUTOSAR, and also the cores here. But it depends on the generated information or the configured information during the AUTOSAR build process. Then we can, for example, enable another breakpoint, go through that breakpoint, and then we'll see, okay, right now we have 2 running tasks in parallel, which is that on core 0, and we have a running task on core 2. The others are suspended again, and we see the others are also in the idle tasks. Then we can look into the stacks. For example, we have different stacks here defined in the operating system. For example, here on core 2, there's a stack assigned to the wait for event from core 0 task. You can right click here on the cells, for example, to navigate to the memory, to look into the stack. We see here this is a direction down. We have a size of 100 hex, and this is the base address here of the stack. And if you have a stack goes down, then the stack starts somewhere here. We see a few values that are pushed on to the stack, and we have here a fill pattern that indicates this area was not used before. So with this fill area, you can, for example, look to your stack utilization. Then we can also look to the task control blocks by using the current task cell here and add this as an expression in the watch window. The watch window shows variables as well as complex structures or expressions here. We can unfold this and look into the configurations for each task. And also if we remove the breakpoints and start the application, then we see, okay, the task changes over time. But this is a very raw view, if you like. So there is a much better way to look at the task changes and to do some measurements and visualizations, and this is based on trace. And that's what I'd like to show you in the next few minutes. Go back to the slides because there I'd like to introduce a little bit or give you some information before I show you the feature. Maybe you know a little bit about tracing. Tracing is basically a hardware feature that allows you to observe the runtime behavior of your system. The typical task or the typical way is to trace the executed instructions and to get the program trace, and from that you can analyze the trace data and see which functions were executed. For task trace, it is a bit different. You need a little more information about the system, where pure program trace is not sufficient here. And for that reason, in RT, there is a hook mechanism defined that allows the operating system to be instrumented. I told you this before. And this instrumentation is in such a way that the trace system and the subsequent analysis of the trace data get all the information needed to represent, for example, the states of the traced tasks, and to show you the state changes. With the work on the AUTOSAR standard, there was implemented a new hook mechanism that is now standardized in the AUTOSAR directly and not in the comes not from the OSEC anymore, and this makes this very lightweight. Or the focus was to make the hook mechanisms very lightweight and also standardized between the tools. The hooks in the operating system are generated automatically during the generation of the AUTOSAR software components with minimal intrusive and with the aim to be compatible and interchangeable and provide interchangeability between the tools. Furthermore, there is also a standardization regarding the export of the trace data so that you can load or use the traced information also in other tools, like timing analysis tools. Compared to the former RT, the RT trace is more detailed. You see here, for example, a state machine of the state of a state that is defined in the AUTOSAR standard. Sorry, and this can now be completely reconstructed by the information provided by the RT file to show these information. The hooks that are used for tracing are automatically generated. The hooks are defined in a so-called RAXML file that describes the complete AUTOSAR system. It is also named as the the AUTOSAR ECU. And as a part of this description, we have all the RT information as a module included. Then we have an RT hook generator here that reads that description and creates the implementation for the hooks. Yeah, basically it's a C file and header file that has to be linked to your application. And this RT hook generator is in the responsibility of the debug tool. And for that reason, in UDE, we have such a RT hook generator that we provide. It can be very easily invoked in the build process. It generates the hook information. You can compile it, and then you can trace based on these hook information. Yeah, it's very simple. As an input, you use the AR.XML file and specify the output files, a C file and a header file, and then put it together and compile your application. And with that, you can now trace the system. I'd like to show you what you can get with that. For example, we are using the execution sequence chart in UDE, and I'd like to show you what you can then see. For that, I need to configure the trace. This can be easily done in the AUTOSAR window by a right-click, configure trace based on the default hook implementation. We can select the task trace. That is the most common selection here, and then you can add also function trace or code trace. This has some limitations, the code trace, especially on the AURIX. If you use an AURIX and the trace system on the AURIX, then you can do only code traces for, depending on the device, for 2 or 3 cores in parallel. So you can't select everything here. You get, the limitation is either core 1, core 2, and nothing more. Then press configure, and then you can start the trace. Application is running. The trace is now configured, the configuration information are written to the target system. I stop the trace manually, and then I start the analysis here in the execution sequence chart. This takes a while because the analysis is not that easy to analyze the captured information, especially if you have a program code in place. And then the results are displayed in the window, and then you can unfold, for example, here the core 0. You see we have here different labels. Zoom to the complete range that we can see something. The labels in uppercase letters are representing the state machine states of the AUTOSAR tasks here. Also the state machine of the interrupts. The color is green that we are using for this information here. If we look at the labels, then we see, okay, we have here a task that is running. If we go a little bit, or zoom a little bit in, that then we see here the ready state of that task. Then we have the information about the running and not running of the traced tasks. For example, here our demo worker task. This is in dark red, and you can now also unfold here the specific tasks. Zoom a little bit. Okay, let's put it a little bit in the middle. So you can see in a lighter red all the executed functions here. And here you can now look into your executed tasks and get an impression what happens on your system during runtime. Of course, you can use this tool also to do some time measurements. For example, if you want to check if the demo worker task is executed periodically, then you can look at the overall timeline, and you can also measure the timing by using the markers in that window. For example, to do so, you use the Shift left click for the first marker and the Control left click for the second marker, and the time between this is nearly 1 millisecond. So this is the 1 millisecond task here. You can also use the traced information for exporting them into other tools. For that, we have export functions in to 3 different formats. The best trace format, BTF. Then we have a special one, which is at the moment goes into the deprecated state because some work has been done in the past to do that a little bit better. For the Incron tool, and the most common way and the state-of-the-art way is to use as an MDF, as an export format, to export trace data that can be loaded, for example, in the Incron tool, as an example, as a timing analysis tool and a much more sophisticated visualization and analysis tool for trace data. Okay, I think time is up. So I'd like to thank you very much for your attention. If you have any questions, drop us an email. Thank you very much.